Hello everybody, Mr. Eck here, you're watching Eck Math, and today we're going to take a look at section 1.2, which is all about the basics of functions and function notation. Before we talk about functions, we're going to talk about relations. A relation is a correspondence between two sets. The set of inputs will be called the domain. These are familiar words, I suspect. And the set of outputs will be called the range. The least formal type of mapping is done using a mapping diagram, which is what we have here. You have some box that shows your set of inputs and some box that shows your set of outputs, and then you might draw arrows that connect the inputs to the outputs. So maybe A connects to 2. They can be curved arrows, they can be straight arrows, it doesn't really matter. Maybe B connects to 1. We can cross over like that. And maybe C connects to both 3 and 4. And that is an example of a relation, where you can specify, hey, for any input, you can find an output. Sometimes more than one output. Some other ways to look at these sets of inputs and outputs, one would be as a table, where you make a column of your inputs and a column of your outputs. This is very familiar to anyone that's made a graph. So you might have an input of A and an output of 2, and an input of B and an output of 1, and an input of C and an output of 3, and this is a little bit of a quandary. I don't really know how to do 2 outputs for 1 input, so you might do 2 lines like that. And you could also describe a relation as a set of ordered pairs, where the input is the first piece of the ordered pair. So you might do A, 2, B, 1, etc. So 3 ways to describe them. You can have relations that map all kinds of things to all kinds of things. It doesn't have to be letters to numbers. Often in math it's numbers to numbers, obviously. But there's no rule that you couldn't have a relationship between shapes and colors, for example. Maybe squares map to pink and triangles map to green. That's a perfectly valid relation. It's just not a quantitative relation that uses numbers. Most of the time in math, we want to look at relations that have one special property, and that is that they represent functions. So what the heck is a function? Well, the book definition, and the one that I'd like to go with first, is that a function is a relation where each input corresponds to only one output. And what this means when you have a relation with this property, and we'll give some examples of this property, is that it is a predictable relation. That is, you always know what output you're going to get. So let's first look at a relation that is not a function. Let's say we had ABC 1, 2, 3, 4, just like we had above, and we had A mapped to 1 and A mapped to 2, and maybe we had B mapped to 3 and C mapped to 4. This is not a very exciting relationship, but the issue is right here with what we did with A. The input A goes to 2 outputs, 1 or 2. So this is an example of a relation defined as a table that is, not as a table, defined in a mapping diagram that is not a function. On the other hand, over here, let's look at relation number 2, which we haven't defined yet, but let's go ahead and say that A maps to 1, B maps to 3, and C maps to 3. Now, is this a function? Well, we fixed the problem with A. A maps to 1. That's fine. But have we created some other problem with B and C? The answer is no, because if we look carefully at this definition, it says a relation where each input corresponds to only one output, and we can still say that A, let's do it as ordered pairs. A went with 1, B went with 3, so B has a specific output of 3, and C also has a specific output of 3. That's perfectly fine in a function. You can have two arrows that point at the same number. You just can't have one input giving two separate outputs. So this is a function. Some people also might say this is not a function because it doesn't cover everything in the range. There's some missing values. Again, doesn't matter. Those properties you're thinking of, one is called the property where two things go to one thing. That's called it not being a one-to-one function. We'll talk about those later. And the property of covering the entire range is called being an onto function. This is stuff you'll see later on in math. And so this function is not 1 to 1, and it's not onto, but it is still a function. So oftentimes people mix those things up. When we say is something a function, we really mean that each input corresponds to only one output, and that's the only rule for being a function. Let's try an example using the ordered pairs really quick. So the question is the relation with ordered pairs 1, 2, 2, 5, 5, 2, and 1, 3 a function? By the way, often when you see these functions as ordered pairs, or relations, as ordered pairs, you see little set brackets around them, so I put those here. So these are the, you try. Pause the video, give this a try, and after you've returned, let's take a look. So we're looking at the inputs are the first coordinate, and the outputs are the second coordinate. And we want to know, does each input represent only one output? Well, right away you might look at the middle two and say, that's suspicious that we have a 2, 5, 5, 2. We can't have that. That's actually fine. 2 can map to 5, and 5 can map to 2 because this 2 is the input, and that 5 is in the outputs, and we just have this situation where we have 2 goes to 5 and 5 goes to 2. And no problems actually are happening here. But there is a problem with these 1s. So in a function, we can't have a repeated input. That's the main issue. So this is not a function. And if you're asked why, because 1 has output of 2 and 3. And just to think about why this is so bad, think about your calculator. When you use your calculator and you press a button and you tell it to do 2 plus 2, you don't expect to get 2 answers. You expect one predictable answer. That's because your calculator speaks the language of functions. When you're completing a multiple choice exam and you bubble in your answer, how many answers do you get to pick? 1. Because in this analogy, that's kind of behaving like a function. There's one correct, predictable answer, and you should always get the same thing every time when you use a function like this. That's different than relations, and it's why functions are useful. It's because you can program them, and they're reliable, and you can create algorithms with them. And that's what most of math is, about reliability and algorithms. Let's take a look at another flavor of question about functions. So this asks us to solve each equation for y, and then determine whether the equation defines y as a function of x. So you really do have to solve this for y. Since we're asking y as a function of x, we're going to talk about that language a little bit more. But when we see that, we do have to solve each equation for y. So the first thing we might do in equation A, here let's just draw a line to keep these separate. First thing we might do in equation A is take away 2x from both sides. And we get y equals negative 2x plus 6. We'll just write it in that way because it's most familiar. We might know what the graph of this is, and that could help us. We'll talk about that later. But right now, basically, you just inspect and think. Do any x's produce multiple y's? And you can look at this equation, and this is a predictable linear equation. There's no funny business going on here. So, no, there's no multiple y's. Which means that this, yes, is a function. Yes, y is a function of x. So that's our first example of something that is a function that's defined with an equation relating y and x. Now let's look at the second one. So we have x squared plus y squared equals 1. Spooky equation. We'll talk about what the graph of that looks like later. You might remember it. Let's take away x squared from both sides. And then we need to solve for y. This has a square on here, so we're going to square root both sides and get y is the square root of 1 minus x squared. But remember what happens when you take a square root. You got to put a plus or minus on it. So this is actually two equations. We could even write it as a set of two equations. Y equals the positive square root of 1 minus x squared, and y equals the negative square root of 1 minus x squared. And guess what? We've figured out what's wrong with this story. For any given x, then, let's try x equals 0, for example. There are multiple outputs. So you could have the positive square root of 1 minus 0, which is 1, or the negative square root of 1 minus 0, which is negative 1. Whoa, this is not a function. Because for the input of 1, so we'll say y is not a function of x, because if x equals 0, y equals 1, or negative 1. And we don't know. And again, if this was on your calculator and your calculator said to you, well, hey, dude, 1 or negative 1 are the answers, you would throw that calculator away because it's not a useful answer. And that's the same idea here. This is not a function. So that's kind of annoying and fiddly to do with just pure algebra. It's certainly possible by solving for y and sort of inspecting. But luckily for us, there is a much easier way. And that easier way, you can see on the bottom of the screen, is called the vertical line test. And that's a visual check for if a graph represents a function. And specifically, this represents if y is a function of x. So what is the vertical line test? Well, let's say this. A graph represents y as a function of x if every vertical line drawn through the graph intersects that graph only once. So this must be vertical lines, and it must be every vertical line. So we're going to look at how that vertical line test applies to the two graphs that we looked at, or equations that we looked at above. And we're going to start by sketching their graphs. So we had 2x plus y equals 6. Well, we know that that's a linear equation, and the best way to graph a linear equation when it's in this form is by using its intercepts. So we think about x and y. We think about if x was 0, what would y be? You can imagine covering that up, and y would be 6. If y was 0, what would x be? You can imagine covering that up, and x would have to be 3, divide by 2. So we go to 0, 6, and 3, 0. And we could sketch the line that connects all those pieces. There it is. May not be exactly to scale, but all we need is a sketch here. We just need to look at a line. And we want to ask ourselves the question, put that back. Does any vertical line that you pass through this slanted line intersect the slanted line more than once? Well, this line only intersects once. This line intersects once. no vertical line is going to touch this more than once. In fact, that's kind of a property of lines, is that they can only ever intersect once. So this is a function, say y as a function of x, because it passes the vertical line test. We can say VLT for vertical line test. All right, let's look at the next one. So this equation is x squared plus y squared equals 1. And for this one, we solved this with some annoying algebra, but you also already know what this graph looks like, I hope, because it is a circle with center of the origin and radius 1. It's of the form x squared plus y squared equals r squared. So let's go ahead and sketch that circle out. Let's say here's 1, negative 1, negative 1, and 1 right here. It's not quite to scale. It doesn't have to be to scale for us to understand how it interacts with the vertical line test. Now, let's take a vertical line and try to pass that through the function. Well, certainly, there are some points where a vertical line does intersect more than once, but that's not what the test says. The test says that every vertical line, or any vertical line, intersects in exactly one point. And in fact, that's not true. This vertical line right here intersects the function 2 times. We also even proved that when we did our algebra right at the start. This vertical line, when x was 0, we proved hit at y equals 1 and y equals negative 1. There were 2 output values, and here we can actually just see them on the graph. So we are going to say that x squared plus y squared equals 1 does not represent y as a function of x because it fails the vertical line test. And if this was a quiz or a test, you might want to explain a little more about the vertical line test, just thinking about the kind of questions we might ask you. So you might say, if you had to elaborate, that it fails the vertical line test because there are some inputs with 2 outputs, like x equals 0 or x equals 1/2, if we say we drew this line at 1/2 right here. No, that's not quite to scale. So that might be a little addition, a thing you can say on there to sound extra smart. And that, my friends, is the vertical line test. Draw a vertical line through the function. If it touches more than once, then that thing is not actually a function, it's just a relation. And there's plenty of relations out there that are nice graphs. Circles are a great example. But most graphs we want to look at are functions. This next section is a little bit tricky, but it's important because it's about language and how we talk about this stuff. So let's look at the function y equals x squared. And I have 2 questions. One is the one you usually ask, which is y a function of x? And there's another question that you might see sometimes, especially later on, which is x a function of y? And those are different questions that have different answers. Let's take a look first at y equals x squared. So the question, is y a function of x? Well, x squared, we know its graph. It's the parabola that opens upwards and looks like this. And it does, so this is y equals x squared, and it does indeed pass the vertical line test. Any vertical line that you draw through x squared intersects the graph of x squared only 1 time. So y is a function of x. Yes. However, if we ask, is x a function of y, switching the order, we need to solve for x. And check out what happens when we do. So we have y equals x squared. And then we might square root both sides, and we get plus or minus square root of y equals x. And all of a sudden, we kind of have a problem. And the problem now is that if x is actually the output and y is the input, which is what happened when we reversed this order, then all of a sudden, say if y is 4, then x is the plus or minus square root of 4, which is 2 or negative 2. So here's an algebraic example that because we had one input and it went to 2 outputs, y was not, nope, said that backwards. X is not a function of y. So I put this in here because often we'll say, this is a function. But it's really more complicated than that because it's more about what variables are the ins and what variables are the outs. And it's important to specify what you mean. Even if 99% of the time x is in and y is out, we still say y is a function of x because it's not always the case that that's true. Now for something kind of different. We've been talking about what is a function, but what about function notation? This is often what you think of as how you use functions. So we have a function defined as f of x. So we pronounce this f of x, which means that x is the input and f of x is like the output. You can think about this as a y equals. Again, that's just another way to talk about inputs and outputs. And we're given the function f of x equals x squared minus 2x plus 7, and they ask us to evaluate each of the following. So x is the input. So when we say something like f of negative 5, what we're saying is let x equal negative 5. That's what we're saying. And we substitute that in. So if f of x equals x squared minus 2x plus 7, then f of negative 5 is, and be sure you put parentheses here, negative 5 quantity squared minus 2 times quantity negative 5 plus 7. Those parentheses are really important because when you square that negative 5, that becomes 25. This minus 2 times minus 5 becomes plus 10. Plus 7 is 7, and that becomes 35. This all becomes 42. F of negative 5 is equal to 42. Okay, let's look at something that's not a number. So often when you're studying functions and like their transformations and shifts and stretches and things like that, you have something like f of x plus 4. So f of x plus 4 means that you replace x with the quantity x plus 4. And you have to simplify. So here I'm going to use the function that was written above and sub in x plus 4 anywhere there was an x. So this is going to be x plus 4 squared minus 2 quantity x plus 4 plus 7. When you do this x plus 4 squared, remember that it's not just x squared plus 4 squared, it's x squared plus 8x. That's that 2ab perfect square pattern plus 16 minus 2x minus 8, distribute that negative, plus 7. And just to clear that out, this is x plus 4 squared is that, minus 2 quantity x plus 4 is minus 2x minus 8, and of course 7 is 7. Let's clean up our terms. So we have one x squared term, we have an 8 and a minus 2x, so that's going to be plus 6x, and we have a minus 8 plus 7, so that's like minus 1, then plus a 16, so that's going to be plus 15. So we're going to say that f of x plus 4 is equal to x squared plus 6x plus 15, and we're done. Let's look at one last thing. And it's this substitution f of negative x, or opposite x. And this is something we're going to talk about later when we do symmetry tests. You can kind of think about this as testing if a function has symmetry to the left and right. If you want to know why, you might plug that in. So you might want to know what happens when you test sort of an x and a generic, its generic opposite. But for us today, we just have to plug this value in. So I'll write out what f of x was. And then we'll write f of minus x. And when we sub this in, the most common mistake is just messing up negatives. So be sure you put parentheses around all those minus x's. So it's minus x quantity squared minus 2 times minus x plus 7. Cleaning this up, negative x squared is like negative 1 squared x squared. So this is x squared. And then minus 2 times minus x, this is, again, like a negative 2 times negative 1 times x. So that's like plus x. And then this is plus 7. So we would say that f of negative x is x squared plus x. I dropped a 2. X squared plus 2x plus 7. And in terms of symmetry tests, what we'd notice is that some things change sign, but not everything changed sign. And so this doesn't actually have any symmetry. We'll talk about that in a later section, just as a note, though. So one of the last things we're going to talk about today is how to find the domain and range of a function or relation. Both have domains and ranges, but mostly functions today. So we've already mentioned these terms, but let's just recap. The domain is the set of all inputs to the relation or function, and the range is the set of all outputs. Often on a graph, the domain then is the set of all x's, but not always. And often again on a graph, the y is the range, the set of all outputs, but again, not always. But that's a good way to at least remember as a start. Let's look at this relation right here, which has just been defined in terms of ordered pairs. So again, when we look at a relation that's in brackets that's defined in terms of ordered pairs, these are the ins, and these are the outs. The second term is the outs. So the domain is the set of all inputs. And in this case, the domain is just the single numbers 1, 2, 3, 4. So I'll write a set bracket and then make the list 1, 2, 3, 4. And the range is a set of all outputs, and the outputs are 1, 6, and 8. And even though there's 2 1s in the range, and again, that's okay, you can have a repeat element in the range as long as it's still a function. We don't write 1 twice, we just write 1, 6, 8, and close our bracket. These don't even technically have to be in order, sets aren't ordered, but it helps at least a reader understand where you're coming from when you put them in order. So that's the domain and that's the range when your function's just defined on single ordered pairs. But most of the time in precalculus, our functions are defined with equations or graphs. And that's what we're going to look on now. So what if we were given the graph and we had to identify the domain and range of this function? So we're going to do ABC here. Let's just look at A real big first. So X is the set of inputs. That's going to give us the domain. And Y is the set of outputs. And that's going to tell us the range. And when I have a graph and it's something I can write on, what I actually like to do is just come to the actual graph and kind of shade on the x-axis everywhere that there's a graph. So looking over here, I imagine I'm taking a walk. I'm walking down the x-axis looking for a graph. Well, there's nothing. There's no graph. There's no graph. Except right here at -2, there starts to be a graph. And I'm going to do a bracket to show that that's included. And then there is a graph all the way up until 1 here, where the graph is right above me. And then further on, there's no graph. So the domain is just from -2 to 1, but instead of inequalities, it is better to write this in interval notation. So we write -2, 1. And we use brackets because that correlates with the less than or equal to sign, just to refresh your interval notation. Let's look at the range. So the range, we do the same thing, except we imagine we're starting on the -y, and we're walking up, la la la, and we shade on the graph everywhere that there is a graph to, in this case, the left or right of us. So starting at 0, there's a graph all the way up until we get to 3. And so the range as an inequality is -1 is less than or equal to y, which is less than or equal to 3, or we can write it as -1 to 3 with brackets. You'll be required to write these as intervals, just as part of the question, but say if you do write them as inequalities and you use the wrong letter, then it's also wrong. So make sure if you're doing inequalities and you're talking about domains and ranges, you're using the right letters for each. Jumping over to number B here, let's again find the domain. Well, in this case, we're walking along the x-axis, and we notice that the first point on the graph is at -2, but it's under an open circle, which means -2 is not included in the graph. Now, if I were to start my range at -1 and shade over, I would be missing an important part of the graph, which is like everything right here. So instead, to fix that, we're going to put an open circle or a parentheses at -2 and say that the entire domain goes from -2 up to 1. So the domain, and I'm just going to do intervals, is -2 to 1. And we do a parentheses because that's what correlates with the open circle, which means that -2 is not included, but -1.99998 is included. Let's look at the range. So for range, we imagine we're walking up y. The first y value we see is -1. We go all the way up, and the last y value we see is 1.9998. So we say that this ends at -2, and we write the range as bracket, because it's the lower number, -1 up to 2, parentheses. One common mistake I see, especially with range, is people writing them backwards. This should always be small to big as your number, whatever your symbols are on the outside. And if you do write it backwards, again, it's wrong. It's not infinitely wrong, but it's wrong. So make sure you're writing them small to big. That's part of the communication part of all of this mathematics, is writing things in the same way that everyone else does. Let's take a look at question C. So this one's a little more interesting. This is called a step function. And it is a function. We can check that it passes the vertical line test. Any vertical line you draw only touches the function once. Even here, you'll notice that, yes, the function is touched at that closed circle, and you might think the function's hit twice, but look at this. There's an open circle there, which means that value's not included at -2. So really, for every x value, there is only one y value, and this is indeed a function. That's the first check. Now let's look at its domain. You might be tempted to say that the domain is something like a series of intervals with a gaps in the middle. You don't do that. You just look at the total shaded area, and so if we start at -3, there is a function all the way up to -2. The function jumps, but there's still a function there. So we just keep on shading until we get to 0, and then we have that open circle, which means the function no longer is there. So we're going to say, we'll write it up here, that the domain is -3 up to 0, inclusive of -3, but not inclusive of 0. That was that open circle. Now, the range on this one's a little spooky. You might be tempted to say that the range is -3 to -1. And we use brackets because clearly there's function here and there, so that's definitely included. And you might want to pause and ask yourself, why is this wrong? This is definitely wrong. Here's why. Did you pause? Here's why. You'll notice that there's not actually function in between those integer values. There's nothing there. There's nothing there. We have a function that's made of gaps. And so in this is a case where we have the domain as an interval, but the range is actually a set of just the single numbers, -3, -2, and -1, because those are the only places where we actually have a graph is just at those specific y values. Let's write it in. -3, -2, -1. And when we have a list of numbers like this, we use curly brackets instead of intervals. And again, that's important. If you list an interval here, it's wrong. Curly brackets, the order doesn't matter, so I'd accept -1, -2, -3. But this is just when you have a single set of numbers. That's how you write those out. To close out today's video, I would like to give you 2 examples of how you find the domain from an equation. It's often harder to find the range from an equation because you usually want to have the graph to find the range, but domain we usually can find from the equation, and it often helps us make the graph. So you may not see this in the section 1.2 homework, but it's just a very useful skill to have in pre-calc, and you're going to need to know how to do it. So in this sense, the domain is the set of allowable inputs. And there's 2 reasons that an input might not be allowable. We'll just say these are the bad things over here. 1, division by 0, or x over 0. And the other, so we'll say div by 0. And the other is square root of a negative number, square root of -2. We'll say square root of a negative. By the way, it's okay to have a negative sign under a square root if it's attached to a variable. That's fine. It just is a sort of a reflection or a transformation. But what you can't have is something like the square root of an actual negative number. That's square root of 2i. We don't know how to deal with that yet. So when we're talking about domain, we're talking about real number domain. And we're going to say that those are not included. So how do you find the domain from an equation? Well, the first thing you do is look at what you're in danger of. Are you in danger of dividing by 0? Are you in danger of square rooting a negative? If you're not, like you have a linear equation or something, you don't worry about this. The domain is all real numbers. Here, maybe let's do an example of that. So say we have y equals x squared plus 2x plus 11. That's a polynomial. There's no square roots. There's no division. So the domain is all real numbers, which, since we're doing interval notation, we write as -infinity to infinity. That's often how you'll see it. You can also use the symbol R for all real numbers. Those are the 2 kind of best ways to write that. Okay, but let's do something where there's actually a restriction on the domain. Let's look at y equals the square root of x minus 3. Now, what are we trying to avoid here? Well, we're probably trying to avoid the square root of a negative. So what we're going to do is actually write an inequality where we set the inside of the square root greater than or equal to 0. By the way, there's a fancy word for the inside of the square root. It's called the argument. It's actually the inside of any function is called the argument, and that's a term we're going to use a lot because it's helpful to have a word for that, so you don't have to just be like, oh, the inside of the parentheses. So we're going to set the argument here greater than or equal to 0. So that looks like saying x minus 3 is greater than or equal to 0. Hey, we know how to solve inequalities. You add 3 to both sides. You don't have to flip the sign, and you get x is greater than or equal to 3. So that means that the domain in interval notation is just the translation to intervals of x greater than or equal to 3, which is 3 to infinity. Boom, we're done. You probably don't have to find the range from this. You'll probably make the graph and then find the range. So usually we just kind of find the domain from the equation. That's what you do if you have a square root, is you set the argument greater than or equal to 0. Now let's look at example 2 on the bottom. I'm going to scroll up a little bit here. So here, what are we in danger of? Let's think carefully. Well, we're in danger of dividing by 0. So we need to avoid that. So in this case, we're going to set the denominator equal to 0 and find what are the excluded values from the domain. We've already done excluded values in a different section. So what we can do is write 2x plus 8 equals 0. Solve it out, take away 8. So these are the values that would cause division by 0. So these are the bad values. And I shouldn't say bad, I should probably say that these are the excluded values, which is the term we've used. But when we write domain, we want to say what x can be, not what x can't be. We're very positive thinkers when we think about domain. We also spell it right. There we go. So to write x can't equal 4, it's kind of annoying, because if you think about this on a number line, you'd have all the possible x's shaded in, shaded in, shaded in, until you get to -4, and you'd have one little hole, and then you'd have all the values shaded in. And so the correct way to write this in interval notation is as follows. -∞ up to -4, parentheses to say we're not going to reach -4, but we'll get almost there, -4.00001, union, parentheses, -4, and this says we're going to skip over -4 and start at -3.999 and continue all the way to infinity. So when you're doing domains and you're excluding just a single value, you have this kind of wacky looking set of intervals with a union in the middle. Ooh, that looks weird. Union in the middle to show that we're just skipping over that single value. And that's what that means, is we're skipping over x equals -4. And you might be saying to yourself right now, Mr. X, surely there's a better way to write that. My sad answer to you is, nope, that's how we're going to do it. There are some other ways. You can use set builder, you can get fancy. We're going to use intervals. This is how you do it when you have to skip a value. Yeah, it's long. You get used to it. All right, everyone. That's it for today. We have talked a lot about functions. We've talked about domain. We've talked about range, graphs, tables, equations, vertical line tests. All you can do now is try some problems. Good luck. Let me know what questions you have, and I'll see you next time.